Good morning, everyone. Today we will start chapter 5, the most important chapter for Physics 1, and this is about the Newton's second law that we already briefly mentioned in chapter 4. So, chapter 5, we start with the equilibrium. That means net force is zero. So basically, because assuming your force is in two-dimensional space, then we have a net for horizontal net force zero, and then vertical net force zero as well. So you have basically two conditions: horizontal net force and then vertical net force is zero. Of course, because this is a Newton's second law, right? Sigma uh, F net x is a max. Sigma F net y is a may, right? So basically you have a two different acceleration, right? So the basic idea is that if the object is in equilibrium, the net force acting on it must be zero, right? So you will use this fact to find the forces that keep it in equilibrium, right? So again, the same idea. You have an orangutan here, right? Weighing 500 Newton, right? Hanging from a vertical loft. So this object is in equilibrium. So then the first step is you have to identify all forces acting on the object that you are interested in. The first force is acting on the first force is acting on vertically upward tension, and then downward force is weight. So then now you can say this is a F net equals zero. So then in other words, you can say F net y is a tension, basically tension minus a W, because W vector is acting downwards. So basically you have a F net y equals T minus W is basically MAY, but because this object is in equilibrium, we can say this is a zero. So then T minus W, which is a 500 Newton, is zero. So then you can say T is a 500 Newton. Right? So very straightforward. And then one example you hear is a road is free to slide a frictionless seat of the ice, right? So then one of the end of the road is lifted by string. The road is at rest. At rest, equilibrium, net force is zero. So what force is acting on this road? Normal force from the surface, and then tension from the string, right? These are only two forces, right? And then it's weight acting at the center, right? So then you can say, I'll call this is T, I will call this is N, I will call this is a W. And then all these three forces are vertical forces. So then you can say F net equals T up, normal force up, minus W equals MAY equals 0, because this is a inequilibrium, right? So the answer is a P, right? But if what happened if the answer is A or C? So then your tension is acting this way or this direction. So then you have to decompose this tension Ty and Tx, right? So then there's no way you can cancel Tx, right? So because the Tx is the only force acting horizontally. So in other words, your F net x is a Tx only, which can be zero, right? That's not possible unless the Tx is zero, right? So the answer is a B. And the similar question, a car with a mass 115 kilogram is being towed by a steady speed. Steady speed, again, very important statement here. Equilibrium, net force is zero. What does that mean? Your MA is zero. So your A is zero as well, right? So then net force is zero, same as a net acceleration zero. So and then this is a delta V is zero because y acceleration is delta V over delta t, right? So then if this is zero, then delta V is zero. So that means that this is a constant velocity motion or steady speed. So steady speed means again delta V zero, again acceleration zero, so net force zero. In other words, again equilibrium, right? So then now, very first step again, you have a object here, and then find out all forces acting on the object. Tension is acting, and then normal force is acting, and then weight is acting, and then friction is acting here, right? And then all net force must be zero. So then they said the friction is a 320, and then mass is a 1500 times g, so 15000. And then normal force, basically we don't know what is normal force. And then tension we don't know, but tension you can decompose this tension two part, which is a Tx and then Ty, where Tx is a hypotenuse times a, which is T times a cosine 20, and then Ty is a T times a sine 20. So then you have a two equation, F net x1. What is the horizontal forces? So you have a two horizontal forces, Tx and 320, right? So then in other words, this is a Tx minus a 320 is a max equals to 0, right? Because this is a equilibrium, right? So then now you see Tx is going to be 320. And then vertical motion, you see F net y equals what? Ty plus normal force minus 15000 equals 0, right? So then now you see Ty, but you don't need this one unless you need a normal force, right? Because you already know Tx is a 30, so that means this is a 320, right? So then T times a cosine 20 is a 320, right? So the T is a 320 divided by cosine 20. Okay? You can get the number here, right? Right? So T is a 340. But again, as I said earlier here, you can, because now you know the Ty, and then you can find the normal force as well. Okay? It is a ask to find it. And again, similar question. This is a in equilibrium, right? So you see this 10 Newton has a two forces, right? Vertical force and then the horizontal force. And then this one also has a vertical force, and this is horizontal force. This is a horizontal force. This horizontal force is a 10 cosine theta. This one is a 10 sine theta. And then this one 10 sine theta as well. This is 10 cosine theta. So your F net x, for example, you have a minus 10 cosine theta plus you have a 10 cosine theta. Of course, this must be 0. And then your F net y, you have a 2, 10 sine theta, one of each of these, right? Minus F is a 0, right? So this F is a W. This is different from this F. So then now you see F is a 2 cosine theta. Sorry, 210 cosine theta, so it's a 20. So the answer is a, oh, sorry, this is the vertical is a, the horizontal was a sine, sorry about that. This is a, no, this is a cosine, this is cosine. They cancel. Vertical is a sine, so 20 sine theta, right? So yeah, so this is gonna be 20 sine, sorry. Sine, right? And dynamics of Newton's second law. So then again, the same thing, right? You have a F net max 0, may 0, especially when it's in equilibrium. But if it's not equilibrium, you cannot say this is 0, this is 0. You must stop here, which is Newton's second law. So then now, yeah, you can read this slides. And same thing. Now we have another example. A putter 46 gram of ball with a speed 3 meter per second. So initial velocity Vi is a 3 meter per second. And the friction exerts a 0.02 retarding force on the ball, right? So this is your ball, that object you are interested in, slowing it down. So we help it reach the hole 10 meter away. So basically you're looking for delta x. It's gonna be slower or greater. So then now you have two things, right? So the vertical motion you see is straightforward. There's a two more force, which is a normal force, and then weight down. So then you can say F net y, normal force of weight is a MAY equals to 0, right? So you can say normal force is the same as a weight, but that's this is your extra information. But the main information you have here at net x. So then when the ball is oh sorry, this is the initial condition. So then the ball is traveling to the right? So again, but you have a weight in the and the net force acting on the ball when it's moving, horizontal net force is what? This is a friction force only, right? So this is a minus a 0.02 Newton. This is the friction force. And this is the only force equals to so MA, where M is a 0.046 gram and then times A. So then your acceleration is going to be minus 0.02 divided by 0.046. So this is your acceleration. Of course, it makes sense because it's a negative, right? So then now you find your acceleration is whatever number you've got from here. And then what else? Because you're interested in when the ball will stop, so your V final is gonna be 0. So then now you have three known variables, and then you keep looking for the fourth variable, which is a delta x. So you have to find the equation that doesn't have a time. So that is a 2ax. So now everything is here, right? Your acceleration is a 0.4345. So then now you have a three variable, v final 0. So v initial is a 3, a you already find, and then this is the delta x. So if you find delta x, you see that's a 10.3 meter, then you will see it will reach to the hole, right? And another similar example we already worked on is here, right? A car with a mass 1500 is being towed by a rope at a 20 degrees. So this is exactly the same as what I had right previously. A friction is a 320 Newton opposite to the car. What is the tension? And the rope goes from the rest, 12 meter per second, right? So this is a VI, this is a V final, and then this is a time. So you already have three informations, right? So then you can find the acceleration, you can find the delta x, right? But now here we are interested in the tension, right? So then you can draw the force diagram again. I don't like this picture. Yeah, this is the better, right? So you have a object, the car, normal force acting up, weight acting downward, friction acting to the left, and this is your tension, right? But again, tension, you can decompose this tension into two parts. One is a Tx, and then the other one is a Ty, right? So then now you have a Newton's second law, F net x first, for example. So minus friction, and then what else you have? Plus a Tx is a max. And this time this is non-zero because the object is not moving at a constant velocity. And then your second force equation is y, where you have a normal force of the Ty of minus W. But this time this is a MAY, but this time this is a 0 because it doesn't move vertically, right? It's a vertical velocity is a constant. So this is what we got here, right? And then, you know what is a tx? Tx is a t times a cosine theta. Ty is a t times a sine theta. So then if you rewrite it, fx is a number, right? Tx is a cosine, and w is a number. So then now you see t, and then from here, right? You can see that as well, right? So then you can see you can have these two equations, right? And then ay is of course 0, right? So then if you use the Newton's second law by component, Tx is a T cosine theta minus friction force is a max. And then n minus a T sine theta minus W, which is the second one, equals to 0. Right? So nx is 0, right? So I think it's kind of confusing because nx is 0, n is only has y component only, right? So that's why you have a t cosine theta minus f. You know, wx is also 0 as well. There's no horizontal component of x, right? So you have this. So then now you can solve these equations, right? For your using calculations here, right? So then you see acceleration. So assuming you still have this, and then you have a f is a known, right? But a is unknown. So you can find again as I talked earlier here, because you know the initial velocity, final velocity, and the t, right? So you have three variables. So using these, you can find the acceleration, right? Final velocity minus initial t. So then your acceleration is 1.2 meter per second. So then now we come back here. We know acceleration is 1.2. So then you can solve for t, right? So where t is 3,300 Newton. Okay, so the examples we go over today is extremely important. Okay, we gotta do this one over and over, and then you will have a lot of examples, homework, and the next exam is mostly about this section. Okay, so make sure you understand, and let me know if you have any question to me. Thank you.